All right, well, hello everybody, and welcome to the workshop on the Outer Planets Unified Search, searching for planetary mission data via the web, given at the OpenPlanetary Virtual Conference on June 23, 2020. My name is Robert French, and I work at the SETI Institute in Mountain View, California. In addition to doing research on the rings and moons of Saturn, Uranus, and Neptune, I'm a co-I of the PDS Ring Moon Systems node and the lead developer of OPUS. As a reminder, this session is being recorded. Questions and comments are welcome, and to ask a question at any time, simply unmute yourself and interrupt me. Please keep yourself muted otherwise. I know that we had a number of people who were signing in today who are very new to OPUS and the planetary data system, so I wanted to give a very, very brief overview of who we are. Hopefully you were also able to listen to Anne's talk yesterday and the GeoNodes talk this morning. So NASA's planetary data system is an actively managed, peer-reviewed, and long-term archive of digital data products that are returned from NASA's planetary missions and Earth-based sources, including Earth-based telescopes and laboratory experiments. It's divided into 6 science nodes and 2 support nodes. You can see the list of science nodes here on the right. There's the geosciences node that we heard from this morning, atmospheres, small bodies, planetary plasma interactions, and cartography and imaging sciences, and then there's us, the Ring Moon Systems node. The other 2 nodes are the engineering node, which is sort of a coordination node, and NAIF. If you listened to Boris's talk on Web Geocalc this morning, he is from the Navigation and Ancillary Information Facility at JPL. The Ring Moon Systems node is devoted to archiving, cataloging, and distributing scientific data sets that are relevant to planetary rings and moons and the ways they interact. As a result, 99% of our holdings are related to Jupiter, Saturn, Uranus, Neptune, and Pluto, and their rings and moons. We support the remote sensing data, which means imaging, spectroscopy, and occultations from Cassini, Galileo, the Hubble Space Telescope, New Horizons, Voyager 1 and 2, and a variety of ground-based telescopes. Our main website, which is listed here, is pds-rings.seti.org and includes a variety of different services that I will briefly introduce you to later. OPUS, which is what we're talking about today, is the web-based search engine of the Ring Moon Systems node. And each one of these key points is very important because our goal is to make it easy to search, discover, and explore the available data, and then to select and download products. And in order to accomplish this, we seamlessly support cross-mission and cross-instrument search using our own metadata and our own preview images. And I want to talk just for a moment about what that entails. Because unified search, which is what we try to supply to our clients, is a very challenging project. PDS-3, which you may already be familiar with, and really the new standard PDS-4, were designed to store metadata, not really to make it easily searchable. A lot of the metadata that's available is irrelevant to most users. This may be things like the temperature of certain instruments or particular telemetry downlink modes that anyone who is doing basic research with the information really doesn't care about, but is present in the PDS labels. On the other hand, the metadata that users actually want to search on is often missing. And we'll talk more about what that type of data is in a moment. Finally, the PDS-3 data sets have countless inconsistencies and quirks that make it very hard for researchers to find data. If you listened to Anne's talk yesterday, you heard her talk about how PDS-3 evolved as new data sets came online. The standards changed rather than having one standard that all the data was forced to fit into. This means that different data sets actually use slightly different types of PDS-3 nomenclature. They have various errors in them, and they have various inaccuracies. And we try to fix all of those things when we make data available for searching in OPUS. So OPUS only provides metadata fields that are commonly used by scientists for searching. We create dozens of new metadata fields that did not exist before that people actually need to do their searching. And as an example of the kind of work that we've gone to, we have 25,000 lines of code whose sole job it is to import the PDS-3 data that already exists and to make it consistent for searching so that you don't have to do that work and have that specialized knowledge that we've had to develop. So when we talk about providing our own metadata, there are several different types of things that we do. One of them is that we do what I'm going to call genericize attributes. So for example, let's say that you wanted to look for imaging just basic camera, 2D framing camera kinds of things. You might do that by knowing that Cassini had a particular camera called the Imaging Science Subsystem, and that Galileo had a particular camera called the Solid State Imager, and that Voyager had a particular camera, and that New Horizons had a particular camera, and do searching on each one of those individually. But wouldn't it be nice if you could simply tell your search engine that you cared about images? Same thing for things like spectral cubes or occultation profiles, perhaps the types of things that were being measured, thermal emission, optical depth, reflectivity, and perhaps things like the particular target that was the object of the observation, which tend to be slightly inconsistent between different instruments, how they're spelled, and how they're referenced. So one of the things that OPUS does is it creates this new type of metadata that makes generic fields like observation type, measurement quantity, and many others that allow you to do searching on the attributes of observations rather than on domain-specific knowledge that you would have to look at it for a particular mission or instrument. The other thing that we do is we create a large amount of metadata which gives you information about the particular observations. This is broken down into two main classes, ring geometry and body surface geometry. In both cases, we compute using information about where the spacecraft was and where it was pointing in space in order to figure out things like, for a ring plane, what's the radius that was in the image, the radius range? What's the longitude range? What is the lighting geometry, phase angle, emission angle, incidence angle? What was the distance to the ring plane? What was the resolution in terms of kilometers per pixel? We do the same thing for every body that is in the field of view. So if you have an image that has Saturn and 3 of its moons, we have information on all 4 of those bodies, giving you things like latitude and longitude ranges, again, the lighting information, distance, resolution, and things like that. And this is information that is available from the Ring Moon Systems Node primary archive for downloading in table form, but we import it all into OPUS so that it is easy to search on. The final thing that we do is we provide our own preview images. And our goal, in terms of making the data very easy to explore, is we want a visual representation as far as what is going on in each one of these observations. So for each type of mission and instrument, we've developed a separate type of preview product that represents the data that's being stored. So for example, for Cassini UVIS, there's the hydrogen deuterium absorption cell. We have a particular type of observation for that. The high-speed photometer, you can see where different data points were recorded. The extreme ultraviolet spectrometer has a spectrum for Sears. The composite infrared spectrometer, it takes a lot of observations that look at different parts of a body or that go across the ring plane, for example, and we draw the paths or the footprints that an observation covers. For things like Cassini, ISS, Voyager ISS, Galileo SSI, we color our preview images by the particular type of filter that was being used. So even though the image itself is in black and white, we can show you easily that this is an image taken through a red filter, a green filter, a violet, ultraviolet, or blue filter, for example. For VIMS, which has multiple spectral channels, we show you what the particular observation looked like in multiple channels. So you can see what it's like in various types of infrared and visual, for example. And same thing for the New Horizons IMFIX instrument. So at this point, if any of you have a spare computer or a spare window and you would like to open OPUS yourself, you are welcome to follow along. I'm going to do a live demo now, which is always dangerous, but hopefully it will work out well. So here's the web address of OPUS. So we start out by just going to the main OPUS web page. And there are a couple of features and the layout that I want to point out first of all. The first one is that there are 4 tabs at the top here that are available. And these correspond to the 4 main functions that you want to do inside of OPUS. You want to search, you want to browse the results of that search, and this little badge number that's next to it tells you how many results are currently available for you based on your search results. You want to add things and download your shopping cart. And again, there's a badge number next to it telling you how many things are in your cart. And finally, there's a detailed tab that allows you to look at the full metadata for any particular observation. And we'll look at each one of these in turn. We have a blog that I post to on average once a month, giving updates about what has been done to OPUS recently. And you can find that by clicking on recent announcements. And here's an example of recent blog posts talking about new features that have been added to OPUS. We have a full help system, and I want to go through this briefly here. So in the About system, we give a little bit of an overview about OPUS, and then we talk about all of the different missions and instruments that we support, giving a little information about each and giving you links so that you can go and find information about those particular missions or those particular instruments. We also tell you where those spacecraft were at different points in time so that you know, if you're not familiar with those missions, you know which ones you might want to look at. If you're reporting bugs or feature requests or anything like that, one of the things that we have down here at the bottom is the version number of OPUS that is currently running and which database is currently being used, and I would recommend including those in any bug report that you want to submit. We have a Getting Started guide, which basically covers all of the things that I'm going to be talking about today. It talks about searching, it talks about browsing, it talks about the shopping cart, and details, and getting help. It's a very short document. I've tried to make it very concise, but I do recommend that if you are somebody who has not been in this talk, would like to learn how to use OPUS, spend the 10 minutes that it takes to go through this, and it will make your life much, much nicer. You'll notice with many of these, you can also open a new browser tab that includes the information not inside of the OPUS window. And you can also download it as a PDF file, which you can then print out yourself. We have a frequently asked questions, which frankly doesn't have a lot of frequently asked questions because not a lot of people have asked questions. So if you have questions that you would like us to answer here, please let me know and I will add them to the list. We have another way of getting to the recent announcements. There's a list of all of the PDS-3 data volumes that we have stored. There is a complete manual for our public API, which is the subject of the second talk today. We have a Citing OPUS section, which gives you information on how to cite OPUS in your own papers or posters. And one of the things that we do is every URL that you have completely encodes the current search that you're doing, including what columns, or what metadata fields you care about, what search fields you've specified information for. It does not include the contents of your cart. But if you copy and paste your URL and send it to somebody in email, or whatever, and they click on it, they will get to the exact same place in OPUS that you were with the same search and same information displayed. These QR codes can then be used on posters. For example, this bottom one here encodes the entire search that I am currently doing. So you could put that on your poster and someone who's walking up to your poster could replicate exactly what you did to find the data that you were using. And finally, there's a Contact Us, which is the same thing as this Questions and Feedback tab over here, which allows you to send us any sort of questions or comments that you may have, and we very much appreciate all feedback that we can get. At the bottom here, there's a link to the main Ring Moon Systems Node website, and here you can find information on ROSE's proposal support. We have a variety of tools that give you orbit information about bodies, various planets and moons, and we have the actual volumes available for direct download. And then we also have our own Twitter feed. This is the @PDSOPUS account. And again, I post occasional announcements here, link to the blog posts, information about what is new in OPUS. So please follow us there. All right, so let's go ahead and talk about the search tab here. On the left-hand side, there are a series of constraint menus. Each one of these has inside of it a series of fields. And the ones that you're seeing here are the ones that are opened by default and are the ones that are always available for all observations. There are other ones that will show up in a minute that are not always present. So for each one of these, the general gives you some very high-level information, including the generic metadata that we've talked about earlier. For example, things like observation type, observation duration, the measurement quantity, right ascension and declination of where the observation was pointed in space. For each one of these, there's a tooltip. If you just hover your mouse over it, you can get full information about what it means and how to use it. PDS constraints is things that are specific to the PDS internal data format. These may not be very useful to you unless you are very familiar with the PDS internals, things like volume ID, product ID, things like that. Image constraints is an entire set of way that we've tried to genericize the concept of what goes into an image. So how long an exposure was, assuming it's a two-dimensional image, there's going to be a shorter edge and a longer edge. So what are those sizes in pixels? How many discrete levels did the camera take, and what type of image it is? Is it a framing camera, a push broom camera, something like that? A second set of generic things that we've produced is information on wavelength. So for example, for any given camera or spectrometer, we have extracted the information about what the wavelength range was for that observation, and we put it in these fields so that you can search on things like wavelength without having to know the details of a particular filter or spectrometer. We've recently added occultations to our holdings, and these are fields that allow you to search on specific information about occultations. These are both space-based and ground-based occultations. And then the surface geometry and ring geometry we'll talk about more later, but these are all of those extra fields that I talked about where you can search on things like longitude, latitude, ring radius, distance, lighting geometry, and as you can see there are quite a lot of fields, and these are all things that we have computed in-house at the Ring Moon Systems node as a value add to our clients. Over here on the right are the two fields that are open by default. There's planet, intended target name. You can see there's a tooltip next to them. Again, it gives you the same information that you would find over here on the left. And there is a label in square brackets, and that tells you which one of the constraint tables on the left this came from, just so that it's easy to find. One thing that is very important, and it's something that the GeoNode showed us this morning, they have something very similar, is these green numbers. And this says, if I were to click on one of these search boxes, how many search results would I get? So for example, if I click on the Jupiter search box, I now have 183,980 results. But notice that the rest of these numbers did not change. And that's because when it is computing how many results you're going to get, it excludes any constraints that are in the box that you're actually looking at. But every other search box is going to have its numbers changed based on what you do here. So for example, if you look down here at these numbers, if I deselect Jupiter, well, those are Jupiter moons, so hopefully you're going to see the same things. But in a minute you'll see that they do change. And you'll notice that the Jupiter automatically opened when I selected Jupiter. So if I select more than one of these checkboxes, so for example, let's say that I were to select Earth, which has 10 observations in it, it's going to do any observations that have either of these planets, either Jupiter or Earth, and so we will end up with 10 more observations up here, 990 instead of 980. So let me get rid of Earth here, and I want to go down here and take a look at Saturn in the intended target name. Now, planet is basically, for any sort of ground-based telescope, is what planet was being observed. And for any space-based telescope, like an actual spacecraft, it was where the spacecraft was in time when it took a particular observation. So for Voyager, Cassini, New Horizons, things like that, Jupiter means that those spacecraft were near this particular planet at the time of observation. So you would expect that if a spacecraft were at Jupiter, it would not be taking images of Saturn. And for the most part, you can see that there are now 0 results for all of these different bodies of Saturn. However, notice that Saturn itself actually has a small number of results, as does Saturn rings. And that means that some spacecraft was physically at Jupiter, but was intentionally taking images of Saturn or Saturn's rings. And that's very interesting. So how do we figure out what spacecraft and what instrument was doing these particular observations? Well, we can do that using these same green hinting numbers. So for example, if we pull up the mission, we can see that these are the particular missions that were taking images at Jupiter. Okay, here's the instrument host name, which at this point the only real difference is that it splits Voyager into Voyager 1 and Voyager 2. And here are all of the different instruments that we support for those different missions. And again, you can see which ones were used at Jupiter. So if we were to go down here and click on Saturn, and then look back up here, you will see that many of those instruments and missions went to 0. And now we can see that there were 3 instruments, Cassini ISS, Cassini UVIS, and Voyager ISS, that were used to take images of Jupiter. So let's go down here and unclick Saturn, and we can do the same thing for Saturn rings, of which there are only 26 images, and we can see that all of those were taken by Cassini UVIS, while Cassini was somewhere in the general vicinity of Jupiter. The last things you can do here are you can reorder all of these so that they can look better on your screen, however you want to order them. Just drag and drop the title. You can minimize them so that they take up less space, and you can get rid of your search terms. Now, the thing that's important about this is that when you get rid of a search term where you haven't made any constraints, nothing happens. But if I were to get rid of a search term where I do have a constraint, it deletes that constraint. So notice that that number of observations is now going to change because I got rid of the Jupiter constraint. Okay, so we're going to start over again here. There is a reset search button down here in the lower left. And I can click on that. It says, "Are we sure?" And we start from scratch. For any of you who have just checked in, just want to let you know that it's perfectly fine to interrupt me with any questions. Just unmute yourself and ask whenever you wish. All right, so I wanted to start doing a real search here. So you may be familiar with the NASA Photojournal, which is a way they use it to curate pretty and basically press release quality images. And the thing that has always personally annoyed me about the photojournal is they don't really tell you where the images came from. So they tell you basically where they were, but they don't give you enough information that you can go and find the actual original data products. So for example, here's one of the moon Callisto, Jupiter's moon. It says, "This color photo of Jupiter's satellite Callisto was made from 3 black and white images. We don't know which ones, we don't know which filters were used." They don't even say they were using filters. They just said they were black and white. "Taken on March 5th, but we don't know what year, from a distance of 1.2 million kilometers." And then it gives us a little bit of information, but it doesn't tell us anything about how to find it. This was taken by Voyager 1. Okay, so how do we find this? Well, one of the things that we can do is we can go and start by searching on Voyager 1. So we knew that that was in the instrument host name, and we can look at Voyager 1, which has 34,000 images in general. And notice once we do that, that there are 2 new constraints that open down here. And this is very important. What's happening is that if every observation in your current set of results belongs to a particular mission or to a particular instrument, then a new constraints menu that is specific to that mission and instrument shows up over here. But if there's even one observation that is from some other mission and instrument, then the constraints tabs will not show up. But notice that it will happen automatically. It doesn't matter whether I actually clicked on Voyager 1 or if I did some other kind of search where the only results were Voyager 1. The Voyager search constraints over here will still pop up. So here are examples of the kinds of things we can search with the Voyager mission. Here are the kinds of things that we can search with the Voyager ISS camera. So these are things like which camera was used, filter name, what the shutter mode was, how usable the lines and samples are, things like that. All right, so let's take a look at what we actually got. So we can go to the Browse tab here, and we can see all of the preview images that we have for the 34,000 results. So as we mentioned earlier, notice that they're color-coded, telling you what type of filter was used. One of the things that we do is we provide what's called infinite scroll. And you've seen this on many other websites in one direction, but we do it in 2 directions. So if I grab the scroll bar here with my mouse and scroll down, it will automatically keep scrolling and keep scrolling and keep scrolling. Okay. The same thing happens though if I go up. If I grab the scroll bar and I go up, it will scroll up, and then it will scroll up more, and it will keep scrolling up. And you could go through the entire 34,000 results by doing this. I find that a little bit awkward. What I personally prefer to do is to use either the arrow keys or the page up and page down keys. So if I use page down, it just keeps scrolling. If I use page up, it keeps scrolling. If I do page down or page up, it goes at bigger chunks. You can also use the mouse wheel, which you can't really tell, but I am using the mouse wheel rather than using the keyboard at this point. And the final thing is there is this slider up here, which tells you where you are in the complete set of 34,000 results. And I can just drag that slider, and I can get to a different place. Okay, but this always tells me what the number is of the top left observation that I have in my set of thumbnails. Now, if I hover over one of these thumbnails, I get some information. One of them is that I get the observation number. This is 18,079 out of this particular set of results. The thing that starts with VG-ISS is what we call an OPUS ID. That is a unique ID that we assign internal to OPUS for each observation. It's something that we use for internal tracking, but you can also use it to keep track of which particular observations you have been interested in. There's also some instructions about how you can click on it to do various actions that we will cover in a few moments. And there is also this little mini menu here that pops up another menu that has various features that we'll also be talking about. Likewise, there are a couple of other little icons that we'll be talking about in a moment. All right, so if you don't want to look at it in terms of preview images, you can also look at it as a table. So up here on the top left, there is a view table. If I click on that, I get all of the information that I care about in a tabular format. Again, I have infinite scrolling in both directions. I have the slider that does the same thing. It keeps the table view and the gallery view in sync with each other. It also has its own little menu over here, and if I hover over one of the little tiny thumbnails, it gets enlarged so I can better see what I'm looking at. We'll talk later about how we can change the particular metadata fields that are being displayed here. Okay, so let's go back to the gallery view and back to the search tab and see if we can figure out what that particular observation was. So we knew that it was from March 5th, so we can start searching on observation time. There are lots of different ways that you can type in dates and times into this field. So there are two fields that we have, the minimum time and the maximum time. Notice that there are, again, green numbers, and this says that based on the current search, which is Voyager 1, what is the earliest observation that we have, 1978, December 11th, and what is the latest observation that we have, 1980, December 15th. Okay. Now, our particular observation was done on March 5th, but there are two March 5ths in here, so I'm not really sure which one it is. Okay. So what we could do instead is we can go down here to Jupiter. If I select Jupiter, it's now going to constrain this particular range to times when Voyager 1 was at Jupiter. And now we can see it goes from December of 1978 to April of 1979. So obviously, if we're looking for March 5th, it's going to have to be the March 5th of 1979. The later observations from Voyager 1 were done at Saturn. So I could just type in March 5th. Okay? Notice that the box that I'm typing in here is yellow. That means that as I have typed, it does not like what I am saying. If I were to hit enter right now, it would turn red. Everything would turn into question marks, and it would say your search has failed. If, however, I then put the year on it, the box turns green, and that says that it's perfectly fine. So now if I hit enter, notice that it normalized the date. I typed it in some fairly random freeform format, but it normalized it for me to be a standard ISO date format of 1979 -month -day, capital T, hour, month, second, and fractional seconds. Okay. Notice there are now 4,000 results that start at this time. Now we know it happened on that particular day. We just don't know when on that particular day. So let's say that we're going to start on that day and we're going to go to the end of the day. Now there are 909 results. We can go browse, and we can see that there were a lot of things that happened on that particular day from Voyager while it was at Jupiter. None of them are particularly looking like the ones that we care about here. So how can we constrain it even further? Well, one of them is clearly that we know that we're looking at Callisto. So if we go in here and look at the intended target, we notice that there were 28 observations on that particular day that were taken by Voyager 1 of Callisto. So if we click on Callisto, we can now see there are only 28 results. And if we go back and browse those, these now start to look very much like the image that we care about. Now, notice that there are high-resolution images and there are low-resolution images. And this is because Voyager had two different cameras. It had a narrow-angle camera and it had a wide-angle camera. The wide-angle camera, of course, is going to do the wide field of view. The narrow one's going to do more of a telephoto view. We only care about the telephoto view because that's what looks like this particular image. So we can go down now to the Voyager ISS constraints that we have available and select the particular camera. So here's the narrow angle, the wide angle. Each one of them took exactly half of the available images, and we can constrain ourselves to the narrow angle camera. Now there are only 14 results, and when we go back, they all look like more or less what we want. All right, so how can we get some more information about these and see close-ups of them? Well, as you hover over, you'll see it says click to enlarge in slideshow mode. So if I were to click on this, I now get a medium-sized image of this particular observation. If I click on it, it will actually pop up a full-size image in a new browser tab. Okay. It also has various metadata, and again, in a few minutes, I'll show you how to select what metadata is displayed here. You can now move from one observation to the next in your result set by using arrow keys down here at the bottom, or you'll have to trust me that I'm using arrows on my actual keyboard. Notice in the background there's this little binocular that moves around, and this tells you which image you are currently looking at. one thing that's important to realize here is that while the individual thumbnails are color-coded by filter, any of the larger preview products are not. So you do not get information from looking at this as to what filter was used. You would have to use some other mechanism. All right, so let's figure out which filters and wavelengths these particular colors correspond to, because we know this is sort of purplish, but we're not really sure exactly what that means. So what we can do is we can go up here and we can select the metadata that we care about. And we do that by first pressing the Select Metadata button. And now on the right are the fields that are already selected. These are the default fields that are present when you start Opus, but you can modify them. So on the left-hand side here are exactly the same things that you saw on the Search tab, the same constraints, and each one of them has the same fields inside of it, except that now, where before you might have just one search field for wavelength, now you have two fields, which are for minimum and maximum. That's not true for all numeric fields, but it's true for most of them. This means that, for example, if I were to look at ring geometry and ring radius, the minimum and maximum are in the entire image, what is the minimum radius that is occupied by any pixel, and what is the maximum radius that is occupied by any pixel. Now, it's not really quite any pixel. We actually subsample the images so that it doesn't take an infinite amount of time for us to generate the metadata, but these are very approximate and will give you a good idea of what is in the actual image. So let's go down and look at the Voyager ISS constraints, and we will look at the filter name. And then we will also go up here and we will look at the range of wavelengths that correspond to that filter. Now, I already know what instrument name I'm looking at. I already know what planet I'm looking at. I already know what target name I'm looking at. I don't really care about the start time and the duration. So I'm just going to kill all of those fields by clicking on the little trash can icon next to them. I can also get rid of a field over here by clicking on the field on the left. I can reorder the fields just like you can with the search fields on the front page. Once again, there are tooltips that you can hover over telling you what the particular fields mean. Okay. Finally, you can either discard all the changes that you've made, or you can save the changes and then they actually take place. If you want to give up and reset everything back to its defaults, you can click on the Reset to Default over here on the left. All right, so now once I do that, if I pull up the slideshow view, notice that I have new metadata fields. I have the filter name, and I have the range of wavelengths from min to max, and these are in units of microns. Okay, so now it is more useful for me to look at them in table view, because now I have the columns that I actually care about. So here are the filters, here's the minimum wavelengths, here's the maximum wavelengths. So I can sort on these fields now by clicking on the headers of the table. So right now we're sorting, you can see right here, we're sorting by actually by start time, which I don't have in my table anymore, and then by Opus ID. If I click on the wavelength column, we are now sorting in ascending order, that's what the little down arrow means, by wavelength. So notice that it now goes from 0.28 to 0.35, 0.43, I could sort in ascending order by maximum column if I preferred. And if I click on it a second time, it will flip between descending order and ascending order. Now, there is another way of looking at what you're currently sorting on, and that is these little indicators up here. Each one of these little, what we call pills, has the name of a field that you are sorting on. It says sort by next to it. So we are sorting on wavelength maximum in descending order. Okay, and then we are sorting after that on Opus ID. The reason that we have Opus ID here to the right after this little bar is that we always add Opus ID to the sort order if it's not already there. And the reason is that if you sort on some field like mission, for example, that may have 1 million responses for any particular mission, we need some way to guarantee the ordering of the results that you get back so that it doesn't come back randomly. And we have chosen Opus ID, which is always unique for every observation, as a way of guaranteeing that deterministic sort order. All right, so there are two things we're sorting on because we chose wavelength max and there's Opus ID. If we look in the table, we can actually get an indication of those things because there is a little 1 in a circle next to the wavelength max, and there's a little 2 in the circle next to the Opus ID, telling us that those are sorted on first and second. And again, if I clicked on Opus ID, it would change which order it's in, and it would change the direction of the arrow here. So it sorts first on wavelength in descending order, and then it sorts on Opus ID in descending order. All right, so that's all we're going to talk about with sort for the moment, but let's talk about how to get more information about each one of these observations. And that is, we have what's called the detailed view, and you can either click on this little eye, or you can pull down the menu and you can select View Detail. And what you get now is a slightly larger preview image, and then you get a lot of information about this particular observation. So the first thing that you get is a list of all of the actual PDS products that are available in the archive for you to download. We have different versions that may be available. Now for Voyager we only have one data set, so it's always the current version, but other ones we'll see have multiple versions. We have raw images, cleaned images, calibrated images, corrected images. We have support images. We have the actual browse images. These are the preview images that we've been talking about. All of these are available for download. So if I were to click on one of these, for example, here's the full-size browse image. There it is. That's what we saw a few minutes ago. I could also click on one of the label files, and this gives us one of the PDS3 labels. So this allows you to download each one of these files one at a time if there's one particular file that you really care about. We'll see in a few minutes about how you can download bulk groups of these products for particular observations and more than one observation. Now, if you scroll down, you'll see here's the information for the metadata fields that you've selected. And then here is all of the metadata that Opus has available for this particular observation. And this is organized by those same constraint tables. So here are all the things in general. In PDS, image, wavelength, occultation. It's not an occultation, so they're all marked as not applicable. Here are all the things related to Callisto. So this is all of the surface geometry, latitude, longitude, distance, resolution, phase angle, incidence angle, emission angle, hour angle. Jupiter is not in this particular observation, but because the spacecraft was near Jupiter at the time, and Jupiter was the central planet, we still give you some information about Jupiter. So this includes things like the distance to the body center, and the resolution that you would have if you were pointed at Jupiter. But most of the other fields are not filled in because Jupiter is not actually in the field of view. Here's the information about the ring geometry. This is Jupiter's ring plane. Whatever we happen to be looking at in the camera, Jupiter's ring plane is out there somewhere, and here's the information about where this entire field of view is intercepting the ring plane. Finally, here's the specific information about the Voyager mission and the Voyager ISS camera. We can go back to our browse results and then go back to the detail page, and it remembers which particular detail we were looking at. It's actually stored in the URL, so if I were to copy and paste this URL into a piece of email, send it to somebody else, and they pulled it up, they would see this same details page that I'm looking at right now. All right, so it is finally time to get to the shopping cart because we would like to actually download some of these images. So there are 6 different ways for us to add things to the shopping cart, just to make sure that there's always one where you need it. First one is, if you look at the little icons at the bottom of an observation, there is a shopping cart with a plus in it. And it has a little tooltip that says Add to Cart. So if I click on that, it turns to a trash can, first of all, which is how I would remove something from the cart. It's highlighted with a blue border, and notice that my cart count has gone up to 1 now. A second thing that we can do is we can look in the little mini menu, and there is an Add to Cart option here, which does exactly the same thing. In the slideshow view, there is a shopping cart so that as you're moving around, you can select what you want to have in the shopping cart while looking at the larger preview images and also while looking at the metadata. If you like using your mouse without having to mouse around so much, you can control click on an observation and it will toggle whether it is in the cart or not. Finally, if we go and look at the table view, there is a series of check boxes on the left-hand side. Check means it is in the cart, and I can check one of those, and that means it is now in the cart, and I go back here, and sure enough, that got added to the cart. And then finally, I can control click on one of them, and that does the same thing as using the checkbox. Now, notice there are 6 things that I've added to the cart, and if I go to the Cart tab, I now have a set of observations which is just the things that is in the cart. Now, the navigation that I can do over here on the right is exactly the same as what I could do in the gallery view. I can scroll around with the mouse, the arrow keys. If I had enough observations, there would be a scroll bar. There's a slider that lets me move around. I can change the sort order. And I can also switch back and forth between a table view and a gallery view. And I can select what metadata I would like to display. Now, the metadata and the sort order are universal. So if you change them on the Cart tab, you will also change them on the Browse Results tab and vice versa. The thing that is particularly different about the Cart tab, though, is all of this information that is on the left. So this is information about what data you've selected and what would happen if you wanted to download it. So the first thing that you see here is the amount of data is 32 megabytes, and this is before it has been compressed in any way. It constitutes 124 total files because each one of these observations actually has a lot of PDS files underlying it. And those are the files that we saw back here on the Details tab, where you may have different types of data that's associated with a particular observation. You may have preview images, you may have geometry information, all sorts of things like that. There are 3 different types of downloads that you can do. The first one is a full data archive. And if I click on this, it will create in the background a zip file that has all 124 files in it. And then it will provide a link for me to download it. So let's just do that. On the lower right here, you can see at the middle of creating the zip file, and then it has provided a link to that. So if I were to click on that, you can't see it because I'm not sharing the right part of my screen, but it would open up an archive with all of those files in it. If I do a URL archive, the thing that's different here is that it does not actually include any of the data products. All it includes is some support files. So in the data archive, support files include a what's called a manifest, which is for each observation a complete list of the files that were included in the zip file, as well as their sizes and their categories. When you click on URL archive, you get that same information, the manifest file, and you also get a file called urls.txt. And this is just a list of the URLs that would be required to download each of these data products. So if you want to download a lot of data, we have a limit on how many you can put into a zip file. It's about 3 gigabytes. If you want to download any more than that, what you have to do is download a file that has the list of URLs in it, and then you can use a command line utility like curl or wget, read it into your favorite Python script, whatever, and download each one of these products one at a time. Finally, you can download a CSV file that's appropriate for Excel or LibreOffice or whatever, that includes the particular metadata fields that you've selected for each one of these observations. That's a good way of getting the metadata information itself if you don't care about any of the actual binary product data. Now, when you're creating any of these data archives or UL archives, you can select what types of data products you would like to include. So here are all the ones that are available for these particular observations that I've selected in my cart right now. These are the same things that you saw on the Details tab. I do not have to download all of these. So for example, if I don't care about the raw images or the cleaned images or the calibrated images, and I only want the geometrically collected images, I can unselect the other ones. Notice as I do this, the size and the number of files that I'm downloading are changing. On the right here, it tells you how many observations, I have 6, are appropriate for that particular type of product, how many files, this is one table file and one label file in PDS3, and what their total sizes are. So as I get rid of calibrated images, for example, I should get rid of 12 files, I should get rid of 7 megabytes worth of data for download. I can also get rid of entire categories, so I don't have to click quite so much, and I can get rid of everything or enable everything. All right, so the final thing that I can do is I can empty the cart over here on the right, and if I do that, it's going to ask me for confirmation, and then everything in the cart is going to go away, and now I can no longer download anything. There are a couple of other ways to download things. One of them is that I can go to the Details tab and I can create a data archive or a UL archive for this one particular observation without having to add it to the cart first. And a second one is that I can use one of these little mini menus and I can download either CSV of my selected metadata, a CSV of all of the metadata that we have available, or a zipped data archive or UL archives, again, just for this one observation. All right, so we're going to start over again. There's a second way to start over, which is I can just click on the OPUS 3 icon in the top left-hand corner. Again, this resets everything but does not change what's in your cart. And at this point, I would like to take just a brief second and ask if anybody has any questions before we go on to our next section.
Hello, my name is Leslie. I missed how you cleaned your card out.
Sure. If you look here, let me add a couple of things back to the cart. On the right-hand side here, in sort of in pale blue, there's a button that's marked Empty Cart. Can you see where my mouse is moving?
Yes, thanks.
Okay, sure. And I'll talk about the other options here in a few minutes. All right, so the next little thing that we're going to do here, and by the way, if people don't have a particular objection, we have a lot to talk about with the Opus UI, and we have somewhat less to talk about with the Opus API. And so I would probably like to run over the Opus UI portion of it by about 15 minutes, and then start the API section at 1:45. So feel free to leave if you have to, but I think that will give people a better treatment of what we have available. All right, so the second thing that we're going to search on here is we're going to look for Saturn's Great White Spot. So if you're not familiar with it, you can actually just Google it, and you will find images that show that there are these periodic storms that happen on Saturn in either the northern or the southern hemisphere, and Cassini happened to be at Saturn when one of these was happening. So it'd be cool to be able to see the Cassini images of this. So here's what we can do. We can start off by saying that we want to know about images. I'm not going to say we want anything Cassini specific. I'm going to pretend I don't even know that Cassini is what has observations of it. I know that this happened sometime in late 2010 to late 2011, but I'm not exactly sure when. So I'm going to start December 1st, 2010, and I'm going to end December 1st, 2011. Okay, notice there are 18,000 images available from any spacecraft or any ground-based of any planet that were taken during this time range. Okay, now what we would like to do is say we would like to specify Saturn as our target. But rather than using it as the target name over here, what I'm going to say is that we would like to use the surface geometry metadata that we've created for Saturn to do our search. So there is a special field over here called the Surface Geometry Target Selector, and it's a very important field. When you click on it, you get a list of all of the bodies that we have surface geometry information for somewhere in the database. Okay? So we want to actually get surface geometry on Saturn itself. So I'm going to click on Saturn. Notice that these are radio buttons, not checkboxes. That means you can only select one of these at once. As soon as I click on Saturn here, I'm now limited to Saturn in my result set, 18,070 images. And also, there is a new constraints field over here that opens up called Saturn Surface Geometry Constraints. And inside of this, it should look fairly familiar, because these are things that are similar to what we saw in the ring geometry constraints earlier. Latitude, longitude, resolution and distance, and lighting geometry. Now, I happen to know, just because I looked it up ahead of time, that the Great White Spot was in the northern hemisphere and was roughly between 40 and 55 degrees of latitude. So I'm going to look up the planetographic latitude of Saturn. And you'll see now that we have a field which is observed planetographic latitude of Saturn. And we have images during that year that start at negative 80 degrees and go up to 88 degrees. That's basically South Pole to North Pole. So I can put 40 degrees to 55 degrees in here, and I am now limited to 2,900 images. Okay. One of the cool things that we can do is this field has a type of units available. So by default, we are entering things in degrees. I can also enter things in radians or hour angles. And if I already have data entered in one of these input fields and I change to a different set of units, it actually converts the numbers for me. So I get the same number of results, just using a different format for the data. So this makes Opus a really expensive calculator if you just want to convert between degrees and radians sometimes. Now, I also want to constrain the longitude because I don't want to look all the way around Saturn. I know the spot was basically in one region. So I'm going to look at the observed longitude of Saturn, and I happen to know that it is somewhere between 230 degrees west longitude to 10 degrees. Now, the thing about longitude is it wraps around, right? Searching from 10 to 230 degrees is very different from searching from 230 to 10 degrees, because you want to go all the way through 0 and then back up to 10 again. There's a note here that says because longitude wraps around, you must specify both the minimum and the maximum in order to get anything useful done. OPUS is smart enough to know that this is a type of longitude, and it will do a search specifically that wraps around through 0. So I can search starting at 230 and going to 10, and it will actually do the right thing, even though it looks like the maximum value is smaller than the minimum value. Finally, I would only like ones that have reasonable resolution. I don't want to be too far away from the planet. I don't want to be too close to the planet. So I'm going to look at what we call the finest observed resolution. And again, each one of these has very long and complicated descriptions if you want all the details about what this particular field means. And I'm going to say I want something that is between 100 and 300 kilometers per pixel. All right, finally, at this point I have 846 results, and I can go look at them. So, very nicely, a lot of them actually have the great white spot on them. Always nice when the search does what you want. We also notice that they are in different colors, and we notice that certain images are kind of damaged, and we'll talk about each one of those things later. Okay, so the red images are not just red. They actually tend to be things like methane, and so they really show up in high abstract, in high relief, what the great white spot looked like. So I would really like to limit my result set to images that are sort of reddish. So how do I do that? Well, as soon as I limited my search here, it knew that all of the results that I had were taken by Cassini. There were no other spacecraft or ground-based telescopes involved. So it opened up down here at the bottom the Cassini mission constraints and Cassini ISS constraints menus for me to use. Now, inside of the ISS menu is the filter. So if I pull up the set of filters, here are all of the filter combinations that were used in all of the observations taken by Cassini in its entire multi-decade mission. So we can see most of them are 0 because they were not used to take these particular images of Saturn, but there are a lot of different filters that were. Here's different methane bands, different continuum bands. There was a blue filter, a green filter, hydrogen alpha, different polarizing filters. This is a real mess, and I would not want to have the domain-specific knowledge to say, well, I care about this band and this band and this polarization and whatever. What I really want is just reddish. So what I'm going to do instead is use that generic metadata that we talked about earlier in terms of wavelength. Okay, so I'm going to pull up wavelength as a search field, and notice that it says now that I can type in either a wavelength or a color. So I can actually say red. And as I do that, it has a database of different types of red. So PDS-4, for example, has definitions of different wavelength ranges. It's giving me nice completions for infrared. We have from the CRC, they have defined wavelength ranges for just red. So I think I'm going to select that one. That seems fine. Okay. Now that goes from, it's a very narrow region of red. What I really wanted was everything that was red or longer wavelength. So I'm just going to get rid of the maximum number and keep the minimum number. Okay, so now at this point, if we go and also notice we have units here as well. These are in microns. I can also do it in angstroms, nanometers, centimeters, and notice that it converts the data for us as we go. Also notice that as you change it, it changes these green numbers to be in the units that you've selected as well. So everything is consistent for this one field. All right, so let's go back and look at our results and notice that everything is kind of reddish now. However, there are still all of these annoying white images, and I'd be really curious to know why there are white images in here that are not red. So in order to do that, let's figure out what filter was used to create these images. So we can do that again. We can start by selecting the metadata fields we care about. We can go down here to Cassini ISS. We can add the filter, and now that will show up in the metadata that we're looking at in the table view or in the slideshow view. Okay, we can also look at the wavelength. So here's minimum and maximum. And again, I'm going to clear out a few of these other things that I don't really care about quite so much. I already know what planet I'm looking at, for example, and what instrument. Okay, so now if I look at one of these red images, it says it's a continuous band filter, which is sort of methane-y, and it is in this particular range of near infrared wavelengths. But now, if I go to this white image that's right next to it, this was taken with the clear filter, and it has a wider range of wavelengths that is actually pretty much the entire visual spectrum. So why is that showing up in our search for things that have a minimum of red, even though the minimum is way down in sort of the bluish green kind of range? All right, so in order to understand this, we have to roll back here to our presentation for a moment, and we have to talk about how we can search on different types of ranges. So a range field is one that can be searched using minimum and maximum values. So there are numeric ranges, things like observation duration, ring radius, wavelength. There are dates and times that we've already looked at. And there are fields that have special formatting. So like a spacecraft clock count might have one of these weird formats, or Cassini orbit number. It goes 0, 0A, 0B, 0C, 03. Okay? But they're still ranges because I can specify a minimum and a maximum to search on. I can't specify a minimum and maximum on a string, for example. That's a different type of field. So in the OPUS database, there are two types of these numeric fields. There are the ones that have just a single value for the entire observation. So for example, for one observation, there is only one duration. It doesn't make sense to have a range of durations for just one observation. There's only one duration of the exposure. There's only one size in pixels. You're not going to have a range of pixel sizes for just one image. The number of spectra in a particular spectrum is just one value. At the same time, there are other fields that have two values, which are a minimum and a maximum. So for example, the observation time, there was a starting time and there was a stopping time for a particular observation. For wavelength, there's a minimum and a maximum that were permitted in the bandpass for a particular instrument and filter combination. For ring radius, if you look at the entire field of view, there was a minimum radius and there was a maximum radius. For things like right ascension and declination, if you look at the whole field of view, there's a minimum and there's a maximum. We abstract away for you a lot of the details about how this works, but there is a slight difference in how you search on these two different types of fields. Whenever you have a single valued range field, my blue line here is basically all available numbers. Just consider that the real number line. And I have a single data value for my observation. So I can specify a minimum value and a maximum value to search on, and either that white dot is in the range or it isn't. And that's how we decide whether or not to return that observation to you in your search results. However, when I have a range that has a minimum and a maximum, we have to consider the different types of overlap that we can do. So here is the minimum and maximum for one observation. Okay, so there's a range of values. So for example, when we were looking at wavelength, it had a range of values from 0.49 to 0.77. And then we have a minimum and max that we search on. So again, when we go back to our search tab, we're searching on something that starts at 0.64 and goes into infinity. So there are three different ways that you can overlap these two types of ranges. And these are all done from the perspective of the data in the observation. So the first one is that any of the data could be somewhere inside of this range. So as long as there's a little bit of overlap somewhere, this result counts as something we want to see. The second thing that we can say is that the data must cover the range completely. So there might be data smaller than the minimum, and there might be data larger than the maximum, but all of the range between the minimum and maximum is covered by the data. And the third thing that we can say is that the data is a strict subset. That means that it is only within the search range. There is no data that spills past the minimum, and there's no data that spills past the maximum. So I've underlined these three magic words here, any, all, and only, because these are things that actually show up in OPUS. Whenever you have a range where you're allowed to make this kind of choice, there is a drop-down box over here that lets you choose which of those three overlaps to specify. And because no one will ever remember exactly what these are, there are two other places for you to look for information. One of them is the tooltip, which gives you a very brief information on what the three mean. And the second one is in the frequently asked questions, where it says, what do any, all, and only mean? And here is a much more thorough explanation like I just gave. So don't feel bad if you can't remember what those three mean. So when we specified any, we allowed any of that wavelength range to overlap with this thing from 0.647 to infinity. And obviously something that started at 0.49 and went to 0.77 overlapped, so we're seeing it. What we really want is we want data that only exists within the range that we specified. So we can specify only here. We lost about 140 observations in our result set, and now you will see that all of the white ones have gone away. All right, so the last thing we have to care about here are all these ones that have these black lines in them. This is problems with the transmission from the Cassini spacecraft to the ground station where data was lost. In some cases, it's also problems with the compression. With Cassini, there is a nice field in the Cassini ISS called missing lines. And that says how many of these lines there are in a particular image. And we can say we want a maximum of 0. Now, notice that this field does not have an any, all, only dropdown. And that's because there is only one value of missing lines for a particular observation, and it makes no sense to specify how two ranges would overlap because we actually don't have two ranges. Now if we go back here and look at our results again, you'll see that all of those ones with the black lines in them are now gone. And here's a very nice data set for us. All right, so lots of other things we can do with this, of course. Maybe we would like to also get blue images. So whenever I specify multiple constraints currently, it always ands them together. This is this wavelength and this filter and this number of missing lines. But sometimes I want to do an OR search. And I can do that by clicking on this little plus sign with the OR next to it and adding a second copy of the same search field. So for example, let's say that I wanted to do anything that is red or higher, or anything that is blue or lower. And again, I'm going to have to use only for that. And now it's just skipping everything that's in the middle between bluish and reddish, so we're not going to get greenish, for example. So now if we go and look at our browse results, now we have some blue things, we have some red things, we don't have any green things. So this is a very contrived example. I just wanted to show you how you can specify multiple copies of the search for a particular field. All right, so again, lots of other things we can do in terms of searching. I'm running a little bit short on time here, so I'm going to skip over a few of the things related to sorting and just give you one little thing here, which is that you can add new sort fields by selecting them with plus sign here. So for example, we are sorting on start time and then by filter and then by wavelength. You can change that order and say we would like to search on filter first and then by start time and then by wavelength. Or you can drag it over and say we'd like to start on filter and then wavelength, and then start time, whatever. So now it's got all the blue ones first, it's got all the red ones later. We could get rid of filter by hitting the little X on it, and now we're searching just on wavelength, and then start time. So there are the fields that are available when you hit the plus sign here are the ones that you have not already used to sort on, and that you have selected as interesting to you as metadata. So if there are fields in here that you would like to sort on that you don't see, you have to go to select metadata and select them. So for example, maybe we would like to sort on distance to Saturn. So now I've added that as a piece of data that we have available. Here's distance to Saturn. And if I go and add it to sort, it's now one of my available sort fields. And I could sort, for example, on wavelength and then distance. So now we get all the large ones first and then followed by the small ones for any particular wavelength. All right, so we can do other things with the cart. Perhaps I would like to add a whole bunch of these observations to the cart, and I don't want to have to sit here and click on them one at a time, which gets really, really boring. So I can add a range of observations to the cart. And there are a few different ways to do this again. One of them is that I can go down here to this little menu and I can say Start Add Range. I get an animation that says this is the start of my range. I get a notification down here at the bottom that says this is where I'm starting. And then I can go to whatever last one I wanted to do. Let's do the last purple one here. And I could say End Add Range. And now all of those have been added to my cart. If I do the same thing on an observation that is already in the cart, I get a Start Remove Range instead. And now if I select a range, it will remove that range. I always personally prefer keyboard shortcuts if at all possible. So if I shift click on one of these, remember control click added the one observation to the cart or took it out, shift click starts a range. So if the thing was already in the cart, this is starting a remove range, and now I can start an add range. All right, so if I go back to the cart tab now, the last thing that I wanted to show you is the recycle bin. So now that I have all of these isolated, it's easier for me to look at them and say, you know what, this particular one is duplicated, or I don't care about it for whatever reason. Maybe it's too low of a phase angle, and I would like to get rid of it, but I'm not sure yet. So in the cart, notice that instead of there being a trash can here, there's a little recycle symbol. And if I click on it, this now goes into the recycle bin, but doesn't go away entirely. There's a little badge here that says how many things are in the recycle bin, and it was subtracted from the list of things to download over here. So it's as if this isn't in the cart, but it's just sort of there as a ghost reminder. Now, if I want to put it back in the cart, I can put this little restore symbol here, and I can add it back to the cart. So I can sit here, I can control click, just like I did for adding and removing from the cart in general. There I'm adding and removing from the recycle bin. I can take a bunch of things and put them in the recycle bin. I can also take a range of things and put them in the recycle bin by shift clicking or using the little drag menu here, ending the range. Those things are now all in the recycle bin. If you look up here, I can now restore everything that was in the recycle bin back to the cart in case I decided that, I didn't like doing all that, so now they're all back in the cart. Or I can remove all those from the cart, and then I can empty the recycle bin. And when I do that, they all go away permanently, and I'm left with the ones that I had not put in the recycle bin in the cart. The one last thing I'm going to talk about with the cart is what do you do if you want everything in the cart? I have 618 observations here. Maybe I just want to download all of them. Well, one thing I can do is I could start a range. I could drag the slider all the way to the end, and then I could end the range there. And if you notice, there are now 618 things in the cart, 618 things in our browse results. Second thing that we could do, though, let me empty the cart, start from scratch, is there's a little menu here. One of the things is add all results to cart. If I click on that, it says, are you really sure? And if I say yes, everything goes in the cart. I will empty the cart one last time. And the final thing that I can do is if I go to the table view, remember the checkboxes on the left-hand column here are things that let you add or remove things from the cart. There is a shopping cart icon at the top, and if you click on that, it does the same thing with adding everything to the cart. All right, and with that, that covered the majority of features of Opus, not every single one, but most of them. I will take a break for a moment and see if anyone has any questions. All right, well, thank you all very much. I'm going to stop the recording.